What would your life be like without computers? No smartphones, no internet, no video games. Sounds horrible, right? But these such important devices are often not understood mechanically. How do these machines actually work? How do they think, process information, and solve problems? Welcome to this quick 15-minute introduction to computer science, where we'll uncover the magic behind the digital world. Whether you're a total beginner or just looking for a refresher, you're in the right place. Let's jump in. Computer science isn't just about coding, it's about solving problems using computers at every level. It covers everything from the fundamental building blocks, transistors and logic gates, up to how computers execute instructions using the von Neumann architecture. Over time, we moved from low-level assembly language, where instructions directly control hardware, to high-level languages with compilers that translate human-readable code into machine instructions. At its core, it's all about efficiency. How can we optimize computations at the hardware level with transistors and logic gates, and at the software level with compilers and algorithms? When people hear computer science, they often think of lines of code scrolling down a screen, mysterious symbols. While coding is certainly a significant part of computer science, it's just one tool in a vast and fascinating toolbox. Computer science is less about the code itself and more about the art of problem-solving using computers as our powerful allies. Computers don't understand English, they use binary, the most basic form of computer code, just 1 and 0. Each 1 or 0 is a bit, the smallest unit of data in a computer. Bits are combined to form bytes, which store characters, numbers, and more complex data. For example, 8 bits make a byte, which is the standard unit of storage. The letter A can be represented in binary with a byte. Computers perform operations using bitwise operations, such as addition and subtraction. Bitwise addition follows simple binary rules, just like decimal addition, but limited to 1 and 0. For example, 1 plus 1 in binary results in 1, 0, carrying over to the next position. At their core, computers are just electrical circuits. But how do these circuits actually process information? This is where logic gates come in. Logic gates are the fundamental building blocks of digital circuits. They take in binary inputs 1 and 0 and produce an output based on a specific rule. The most common logic gates include AND gate, outputs 1 only if both inputs are 1, OR gate, outputs 1 if at least one input is 1, NOT gate, flips the input if it's 1, it becomes 0, and vice versa. By combining these gates, we can create complex logic circuits that perform calculations, store data, and make decisions. These circuits are what allow a computer's processor to function. Now let's talk about how computers are actually designed. Most modern computers follow the von Neumann architecture, a model proposed by John von Neumann in the 1940s. This architecture consists of a central processing unit, CPU, the brain of the computer that processes instructions, memory, RAM, stores data and instructions for quick access, input-output devices, allows interaction with the computer, keyboard, monitor, etc., a single storage for instructions and data. Unlike earlier computers, which had separate storage, von Neumann's model allows flexibility by storing both instructions and data in the same memory. Why was this such a game changer? Before von Neumann's architecture, computers had to be physically rewired to change their instructions. This new model made it possible to store programs in memory, allowing computers to be reprogrammable, flexible, and much more powerful. The introduction of the control unit and the arithmetic logic unit, ALU, within the CPU further streamlined processing. The control unit fetches instructions from memory, decodes them, and executes them using the ALU for mathematical and logical operations. This structured approach ensures that computers can handle a wide range of tasks efficiently. Another crucial aspect is the concept of the stored program computer, which means that a computer's program instructions are stored in memory alongside data. This enabled computers to run multiple programs without requiring physical modifications, paving the way for modern multitasking and software applications. Von Neumann's model also introduced a potential limitation known as the von Neumann bottleneck. The speed at which data and instructions are transferred between memory and the CPU is a key constraint in computing performance. Many modern advancements like caching and parallel processing are designed to overcome this bottleneck. This architecture is still used today in everything from your laptop to your smartphone. It forms the backbone of modern computing. Now that we understand how computers process data, let's talk about how they actually solve problems. This is where algorithms come in. An algorithm is just a set of step-by-step instructions designed to perform a specific task. Think of it like a recipe. Follow the steps, and you get the result. Computers use algorithms to sort data, search for information, and perform calculations. Let's consider a real-world example, making a sandwich. Here's an algorithm for it. Take 2 slices of bread, spread peanut butter on one slice, spread jelly on the other slice, put them together. Enjoy. Simple, right? Computers follow similar logical steps, but much faster and on a much larger scale. There are different types of algorithms, but 2 of the most common are sorting and searching. Sorting algorithms. These help organize data efficiently. Let's say you have a list of numbers and want to arrange them in order. Here are 2 common sorting methods. Bubble sort compares adjacent numbers and swaps them if they're in the wrong order. It repeats this until everything is sorted. Quick sort breaks the list into smaller parts, sorts them separately, and then merges them efficiently. Sorting is used everywhere, from organizing files on your computer to ranking your search results online. Searching algorithms. These help find specific data quickly. Imagine flipping through a dictionary. Instead of checking every page, you jump to sections based on alphabetical order. Computers do this too, using algorithms like binary search, which cuts the search space in half with each step. For example, if you're looking for the number 42 in a sorted list, binary search would first check the middle number. If it's too high, it eliminates the top half and searches the lower half, repeating until it finds 42. Algorithms power everything in computing, from how your phone unlocks using facial recognition to how social media apps recommend content. The more efficient an algorithm, the faster and more effectively a computer can complete a task. So next time you write code, remember, you're not just programming, you're designing solutions. Algorithms are at the heart of computer science, making everything we do with technology possible. Now that we understand how algorithms work, let's talk about how we actually give instructions to computers. This is where programming comes in. Programming is the process of writing instructions that a computer can follow. But computers don't understand English or any human language. They operate using binary. So how do we bridge that gap? Through programming languages. Over time, programming has evolved from low-level machine code, which is written in 1S and 0S, to high-level languages that are easier for humans to understand. These high-level languages like Python, Java, and C++ use syntax similar to English and rely on compilers or interpreters to translate our code into something the computer can process. Let's look at some basic programming concepts that form the foundation of almost every language. Onto variables. Think of a variable as a labeled container that holds data. For example, in Python, we can store a name by writing the variable name and then assigning the name in a string. This assigns the text Alice to the variable name, and when we print it, the computer displays the stored value. 2. Conditionals, if statements. Computers need to make decisions. If statements allow a program to execute different actions depending on conditions, such as getting the program to check if x is greater than 5. Since it is, the message prints. 3. Loops. Sometimes we need to repeat an action multiple times. Loops help automate repetitive tasks. Loops can repeat tasks such as printing hello 3 times. Loops are essential for everything from counting to processing large data sets. We've covered a lot in just 10 minutes. From understanding how computers process data, to algorithms, to programming, computer science is an incredible field that shapes the world around us. Whether you want to become a software engineer, data scientist, or just understand the technology you use every day, computer science provides the foundation. The key takeaway: computers are powerful, but they rely on us to give them instructions. Learning how to think like a computer scientist helps us solve problems, improve efficiency, and create amazing technology. So what's next? Keep exploring. Try writing a simple program, experiment with algorithms, or learn more about how computers communicate. The possibilities are endless. Thank you for joining.